Ever wondered what really happens when you press Start Game? From the vibrant worlds of Minecraft to the intense realism of Call of Duty, video games aren't just pixels moving on a screen, they're complex systems powered by cutting-edge technology. Today on Knowledge Hub, let's dive deep into how games actually work. At the heart of every video game lies the game engine, the framework that brings everything to life. Think of it as the brain of the game. Engines like Unreal, Unity, and CryEngine handle all the heavy lifting, rendering graphics, simulating physics, processing input, and managing audio. When you see your character jump or an explosion ripple across the screen, that's the engine calculating hundreds of operations per second. Before diving deeper, it's worth noting that games come in many forms: PC, console, handheld, mobile, and even cloud-based. PC games often push the limits of graphics and performance, allowing players to tweak settings for maximum realism. Console games, like those on PlayStation, Xbox, or Nintendo Switch, are optimized for specific hardware, offering consistent performance and controller-based gameplay. Handheld consoles, such as the Nintendo Switch Lite or Steam Deck, bring console-quality experiences on the go. Meanwhile, mobile games prioritize accessibility and touch controls, using lightweight engines like Unity to run smoothly on smartphones. And now, cloud gaming, powered by services like NVIDIA GeForce Now and Xbox Cloud Gaming, streams games directly from remote servers, removing the need for powerful local hardware entirely. Each platform has its strengths, but all share one goal: delivering an immersive, interactive experience to players anywhere, anytime. Now let's talk about what happens inside your device when you play a game. The moment you launch it, the CPU, GPU, RAM, and storage all come together in perfect synchronization. The CPU, Central Processing Unit, acts as the control center, executing the game's code and managing logic, physics, and AI. The GPU, Graphics Processing Unit, handles the heavy graphical computations, drawing environments, rendering lighting, and animating characters at high frame rates. RAM, Random Access Memory, stores temporary data like textures, object positions, and active processes so the game can access them instantly, ensuring smooth performance. Meanwhile, your storage drive, whether SSD or HDD, loads the assets, models, and sounds into memory. On consoles and PCs, specialized APIs like DirectX, Vulkan, or Metal allow the game engine to communicate efficiently with the hardware. In simple terms, your device becomes a miniature simulation machine, continuously calculating physics, rendering visuals, and processing your actions in real time, frame after frame, often millions of times per minute. Now that we understand the hardware working behind the scenes, let's dive deeper into how the visuals themselves are created. Games use something called a rendering pipeline, which converts 3D models made of polygons into the 2D image you see on your screen. The GPU plays a huge role here. It calculates lighting, shadows, reflections, and textures using shaders, tiny programs that control how surfaces look under different lighting conditions. Real-time rendering means these calculations happen every frame, usually 30 to 120 times per second, to keep the game smooth and lifelike. Next, there's physics. Ever thrown a grenade in a game and watched it bounce off a wall? That's not magic, it's the physics engine at work. It simulates the laws of motion, gravity, and collision detection so the virtual world behaves like the real one. Games like Battlefield or Half-Life 2 use advanced physics libraries, such as Havoc or PhysX, to achieve realism in destruction, object interactions, and even character movement. Then comes input processing, the bridge between player and machine. Whether it's a controller, keyboard, touchscreen, or VR headset, your actions are translated into digital signals that the game engine interprets instantly. Press jump, and your input triggers an event in the engine that tells your character to leap, complete with an animation, sound, and sometimes even camera motion, all synchronized in milliseconds. And we can't forget AI. Artificial intelligence gives life to non-player characters, NPC, making them react, plan, and adapt. From enemy soldiers flanking your position to shopkeepers responding with dialogue, AI algorithms use decision trees, pathfinding, like AI algorithms, and machine learning in newer titles to make gameplay dynamic and challenging. Behind all of this is game logic, often written in programming languages like C++, C#, or Lua. This code defines the rules of the world, how damage is calculated, how items work, and what happens when you complete a quest. It's the invisible script that ensures the game plays the same way every time, no matter who's behind the controller. Finally, sound and music. Modern games use real-time audio engines like fmod or WWise that layer ambient sounds, footsteps, gunfire, and background music based on player location and environment, adding emotional depth and realism to every scene. In short, video games are a symphony of software, art, and science, rendered in real time by GPUs, simulated by physics engines, driven by AI, and held together by thousands of lines of code. So the next time you play your favorite game, remember, you're not just playing, you're interacting with one of the most sophisticated pieces of technology ever created. If you have enjoyed this deep dive about how games work, don't forget to hit that subscribe button for more deep dives into the tech that shapes our world. And as always, stay curious.